Hello everyone, so let's look at some precipitation reactions. And in this example, we're told kidney stones can be thought of as consisting mainly of calcium oxalate, and we're told that the KSP for calcium oxalate is 2.3 times 10 to the negative 9 at 25 degrees Celsius. And then we're asked a couple of questions about calcium oxalate. Alright, so the first question is, a sample of blood plasma contains a certain amount of calcium 2 plus and a certain amount of oxalate anions. Will a precipitate be formed given these concentrations? So let's first think about what are the conditions that need to be fulfilled. So right, we have calcium oxalate and we're given a KSP for that. So that means there is a solubility equilibrium for this calcium oxalate that we can write down. So calcium oxalate solid will be in equilibrium with the two ions, which is calcium 2 plus, right? Because there's one calcium for every oxalate anion. The oxalate anion has a charge of 2 minus. So that is our solubility equilibrium that we are interested in. And that has a KSP that we are given. KSP equals to 2.3 times 10 to the negative 9. And we can also write from our equilibrium, we can write that this is equal to the concentration of calcium 2 plus at equilibrium multiplied by the oxalate anion concentration also at equilibrium. Now, to determine whether or not a precipitate will form, we can remind ourselves that we can use the reaction quotient, similar, the ion product, that's the thing I was looking for, the ion product, the QSP, to compare to our KSP and to see whether or not a precipitate will form. The equivalence of the equivalent parameter, that's the word I was actually looking for. The equivalent parameter to the reaction quotient, which is the ion product, QSP. Right, we can calculate that for our situation. So the ion product, which we call QSP, is equal to the same expression as KSP, but just non-equilibrium concentrations. So that's equal to calcium 2 plus multiplied by C2O4 2 minus. All right, that's QSP. And we are given that a blood sample contains these two different concentrations of those two species. So 0.0025 molar calcium 2 plus and 1.0 times 10 to the negative 7 molar oxalate. And if we multiply those two together, we get a value of 2.5 times 10 to the negative 10, which is indeed less than 2.3 times 10 to the negative 9. All right, which is equal to KSP. So our QSP, our ion product, remember, so it's called the ion product for solubility equilibria, is less than our KSP. And when Q is less than K in terms of solubility equilibria, then it means that no precipitate will form. In other words, we can still continue adding ions to this solution until a precipitate forms, right? So until we reach the equilibrium concentrations is essentially what this Q tells us. So it's like the reaction quotient. It tells us we can still favor the forward reaction until we reach equilibrium, until we reach the saturation point. So we, at this point, for this specific combination of concentrations, no precipitate will form. Right, because Q is less than K. For precipitate to form, your Q needs to be at least equal or larger than K. Q equals to K, technically your solution is saturated, so it's like on the brink of precipitation. So it's technically, there's not a precipitate yet, but you could say that anytime that Q is equal to K or larger than K, I mean, that's it's debatable. So larger than K, definitely a precipitate will form. Equal to K, the solution is saturated, so it's like on the brink of forming a precipitate. Less than K, then no precipitate will form. All right, so less than K, no precipitate. Larger than K, precipitate. Equal to K, solution is saturated. So I still actually would say no precipitate will form when Q is equal to K. All right, going to B, we're asked to say a blood sample has a concentration of calcium, which is given in milligram per liter. What value of the oxalate anion is required to initiate precipitation? So in this case, we're given a concentration of one species, and then we're asked how much of the other species is required to induce precipitation. All right, so in this case, we're basically asked to use KSP to calculate what will force a precipitate to form. So our first step is to convert this calcium 2+ to molar, right? Because hopefully you've recognized that this concentration unit that we were given is not in a molar quantity. So we're given milligrams per liter, and that means that milligram calcium per liter. So we can take that to molar, saying there's 1 gram in 1,000 milligram, right? And then we can do, we convert grams to moles. So there's 40.08, what do I want to do now? Yeah, there is 40.08 gram calcium, right? And that means calcium 2+ in 1 mole of calcium 2+. And this gives me a value of 1.0 times 10 to the -3 molar. Right. So now the question is, what concentration of oxalate would mean that a precipitate will form? So we can calculate the concentration of oxalate, C2O4 2- multiplied by calcium 2+, all right, needs to be equal to KSP. That we remember from how we wrote KSP. So we had that there. So if we solve this for the concentration of oxalate, 2-, sorry, that should be a minus there, minus, then it means that KSP divided by the concentration of our calcium will give us the concentration of oxalate that will cause precipitation. So 2.3 times 10 to the -9 divided by 1.0 times 10 to the -3 is equal to 2.9 times 10 to the -6 molar. All right. So that means if the concentration of oxalate is that, then we should initiate precipitation. Now in principle, this is when QSP is equal to KSP, so then the solution is saturated, so it's the point at which precipitation will start. So, I mean, that's that weird little technicality on it, but we are all happy, everyone's happy that that is the point where we initiate precipitation. So don't break your head on that. It's only when QSP is less than KSP that definitely no precipitate will form. Okay. So we can move on to C. Calcium 2+ triggers blood clotting. So when blood is donated, the receiving bag contains a solution of sodium oxalate to precipitate the calcium oxalate. We're told that we then have a 104 milliliter blood sample that contains a certain mass per milliliter calcium ion. This is placed in contact with 100 milliliter of a certain concentration sodium oxalate solution. And we're asked, will a precipitate form? So let's just think about what's going on here. So it means we have a bag of blood. Well, that sounds terrible. So we have a bag of blood that contains a certain amount of calcium 2+, or it has the volume of 104 milliliter, and it has a concentration of calcium 2+ in it. We're given that as 1.0 times 10 to the negative 7 gram calcium 2+ per milliliter. Alright, and to that we add a different mixture which contains a certain amount of sodium oxalate, which is 100 milliliter, and the concentration sodium oxalate is given as 0.1550 molar. All right. So the question here is, what are we actually then doing, right? So we're mixing these two things together. So we're mixing together a certain amount of calcium with a certain amount of the oxalate. And those two things will be in a new volume, right? Because we're mixing 104 milliliter with 100 milliliters. So that new volume will be 204 milliliter. And that means we will have two concentrations of these two species that we mix together. And what do we need to do to determine whether or not a precipitate will form? We need to take those new concentrations and we need to determine the ion product, the QSP. And if QSP is larger than KSP, then we know a precipitate will form. All right, so let's first just model this as we would normally to say that we mix this thing with this thing and it's in a new volume, right? What are the concentration of the ions? So what is the information we're given? So first, for the calcium, we're given the volume of the calcium and the concentration of the calcium, right? And you see that the calcium concentration is given in grams per milliliter, so we're given a mass per milliliter. So that means we can determine the mass calcium ion from our concentration calcium 2+ multiplied by the volume of calcium 2+. So if we do that, we take the 1.0 times 10 to the negative 7 gram per milliliter and multiply it by 104 milliliter. Then the value that I get here, you end up with 104 times 10 to the negative 5 gram calcium 2+. Right, the units cancel. We just cancel the milliliters, so that means we're just left with gram calcium. That's what we're left with here. Okay, and we can convert that to mole calcium because that's a more useful unit for us. Mole calcium, in that you take, of course, the mass of calcium 2 plus, divided by the molar mass of calcium, which is 40.08 gram per mole, and then I get 2.59 etc. times 10 to the negative 7 mole calcium 2 plus. Okay, so that's calcium. That's how many moles of calcium we have in this bag of blood over here. How many moles of the, what do you call this thing again? The oxalate do we have here? So how many moles of C2O4 2 minus do we have? Well, that we can calculate directly from our concentration and volume that we're given, because the volume and the concentration here is luckily in molar, so mole per liter, and we're given milliliter, so we can just convert that to liter. So I get this as 0.0155 mole C2O4 2 minus. And remember, even though you're given the salt concentration and concentration, the salt gives rise to 1 mole of oxalate for every 1 mole of the salt that is dissolved, right? So that is why it's directly proportional. Right, so that's the number of mole. So what can we get from that for each of these? Now, once we've added these two solutions together, they form a total volume, so a V total of 104 milliliter plus 100 milliliter. All right, and that means we have a new solution volume of 204.0 milliliter. Cool. Therefore, our calcium has a concentration which is equal to the number of mole of calcium 2 plus divided by this V total. Right, of course you need to convert it to liter, so that's what, 0.204 liter. And we also have a concentration of C2O4 2 minus, which is also just equal to the number of mole of C2O4 2 minus divided by V total. Alright, and then you can calculate each of these. So the concentration of the calcium is 1.27 times 10 to the negative 6 molar, and the oxalate has a concentration of 0.075 molar. Alright, so now that we have that, how do we determine whether or not something forms a precipitate? Well, what forms a precipitate is, of course, or indicates to us that, is we must calculate the QSP. And QSP is equal to calcium 2 plus concentration multiplied by C2O4 2 minus. Alright, so we've calculated both of their concentrations. So we put in those values, 1.27 times 10 to the negative 6 and 0.075. Alright, this gives me a value of 9.66 and so forth times 10 to the negative 8. And if we compare that to our KSP is 2.3 times 10 to the negative 9. So this is bigger than 2.3 times 10 to the negative 9. So that means that QSP is larger than KSP. So what does that mean? That means yes, a precipitate will form. Alright, because our ion product is larger than our equilibrium solubility product. Alright, so that's the basics of it. So you can calculate, you can use KSP in different ways. You can use the ion product to predict when a precipitate will form, and you just need to be comfortable with calculating concentrations as normal. Cool. I'll see you in the next video. Thank you for watching.